Welcome to my screencast, which is going to be reviewing the content of lectures 13 and 14. And in those lectures, I talked to you in depth about nucleophilic substitution processes. So just to review what we mean by nucleophilic substitution, if we have a nucleophile, in this case sodium hydroxide, reacting with an electrophile that contains a good leaving group, like this iodide group here, then overall you're going to get a substitution process whereby the nucleophile displaces the leaving group in this molecule here to give the substitution product. So this hydroxide anion will form a bond to this carbon and kick the iodide out of the molecule to give us methanol, which is our substitution product. Okay, so this is what we mean by nucleophilic substitution. And in the lectures we looked at the mechanisms by which this can happen. So there's two. There's the SN1 mechanism and the SN2 mechanism. We looked at which mechanism would happen and why, and we also looked at the stereochemical implications of each of these mechanisms here. Okay, and this is what I'm going to review for you in this screencast. So I'll start by looking at the SN2 mechanism. So SN2 stands for substitution nucleophilic, and the really key term here is this 2 here. What this tells us is that if a nucleophilic substitution is happening via an SN2 mechanism, that mechanism is second order or bimolecular at the transition state. So if we put this reaction up again here, this reaction does actually go via an SN2 mechanism. And because of this, it's been found that the rate of this reaction is directly proportional to the concentration of the nucleophile, and it's also directly proportional to the concentration of the electrophile. So in both instances, if you double the concentration of the nucleophile, you double the rate of the reaction. And if you double the concentration of the electrophile, again you double the rate of the reaction. So this tells us that an SN2 mechanism is obviously second order. It tells us that both the nucleophile and the electrophile are involved in the rate determining process in this mechanism. So if you look at the energy profile for a classic SN2 mechanism, you have your starting materials here at this energy level. Then of course you have your products here at a lower energy level, so this is a nice exothermic process. But what you've got as you go from starting material to product is you've got this energy barrier that you have to get over. Okay, so this is the activation energy, and the reason you have to get over this energy barrier, that the energy initially goes up in the first instance, is that you pass through a high energy transition state, and it's passing through this transition state that is the rate limiting process in this reaction. So we really need to understand this transition state to fully understand the SN2 mechanism. So now I'll actually put up the SN2 mechanism for you now. So here's a classic electrophile here. And if this reacts with a strong nucleophile, like sodium hydroxide, via an SN2 mechanism, what you see is attack of this nucleophile on the rear of this molecule, so to the rear of the leaving group. And you get this bond forming process, so the bonds forming between the oxygen and the carbon, and at the same time you kick the leaving group out of the molecule. And as I said to you in the lectures, this is a concerted process. This bond is forming at the same time as this bond is breaking. So what we can show in the transition state is basically the halfway point in this process here, where this carbon-oxygen bond is forming, as shown by this dotted line. It's not quite complete yet, at exactly the same time as this carbon-bromine bond is breaking. Okay, so this is exactly the halfway point, and this is that high energy transition state that I talked to you about on the previous slide. So because it's a transition state, we put it in square brackets, and we give the transition state symbol here. And it's the passing through this transition state here that is the rate limiting step. And we can see that both of these molecules here, this hydroxide and this alkyl bromide here, both of these molecules are actually involved in this transition state. Okay, so this is the key observation from an SN2 mechanism. So we can then put the product up, and we can see that now this oxygen carbon bond has completed its formation here. So we've got this solid bond here, and the bromine has left the molecule, and now we've got our substitution product. So that's a classic SN2 mechanism there. And when we're drawing these SN2 mechanisms, we always show this halfway stage here, this transition state, which actually corresponds to this energy maxima point in the energy profile of this reaction. And because both of these molecules are involved in this transition state, they're both involved in the rate limiting process. And that's why these mechanisms are second order. So I also talked in the lecture about sort of the evidence for this mechanism. And there's 3 bits of evidence that we've got. The first bit of evidence was what I showed you a few slides ago, that the rate of the reaction is dependent on both the concentration of the nucleophile and the electrophile. So there's the evidence that both of these are involved in the rate limiting step. The second bit of evidence is the effect of steric hindrance around the carbon bearing the leaving group. And the reason that this provides evidence of an SN2 mechanism is that in the SN2 mechanism, the nucleophile always has to approach the molecule from the rear of the leaving group. So this is the angle at which the nucleophile has to approach if it's going to form a bond here and displace the leaving group. And therefore it has to pass through the 3 substituents that are on the carbon bearing the leaving group. And as a result of this, the size of these R groups here greatly affect the ease of approach of the nucleophile, and therefore the rate of the reaction. So if I actually put up some data here, these are relative rates. So obviously the fastest SN2 mechanism will happen if you've just got a methyl group where the 3 R groups are just hydrogens, the smallest groups you can possibly have. Then if you have a primary alkyl halide where one of these groups is an alkyl group, you can see that the reaction rate actually drops off quite significantly. And the reason being that this larger alkyl substituent on the carbon gets in the way of the nucleophile's approach quite significantly, and that's why you see this drop from 30 down to 1. Then if you were to put another alkyl group on the carbon bearing the leaving group, you see a really significant drop in the rate of the reaction. And now because you've got these 2 big alkyl groups on this carbon here, it's very hard for the nucleophile to get through and bond to this carbon here. And then finally, if we actually have a tertiary alkyl group where we've got 3 alkyl groups attached to this carbon, we can see that effectively the nucleophile is not going to get through these 3 bulky substituents on this carbon, and it can't get to the appropriate carbon to do this nucleophilic substitution process. So because the degree of substitution of this carbon has such a great effect on the rate of these SN2 mechanisms, that's a good bit of evidence that the nucleophile is having to approach from this specific angle through these 3 R groups here. The third bit of evidence for the SN2 mechanism is the stereochemical outcome of these reactions. Now, if you were to take S2-bromobutane, so this is enantiomercury pure starter material, and react it with sodium hydroxide, because this substitution process goes via an SN2 mechanism, it actually occurs with complete inversion of configuration to give R2-butanol, and that is a key stereochemical consequence of the SN2 mechanism that we need to explain a little bit more in detail. So I'll go through again this SN2 mechanism with you, and we'll pay particular consideration to the stereochemistry now. So obviously the first step in the SN2 mechanism is the attack of the nucleophile from the rear of the leaving group, and as this nucleophile approaches this carbon, it starts to repel the 3 substituents that are already on that carbon there. So and it's this repulsion of these 3 groups that is the key to this inversion of configuration in this concerted mechanism. So if we show the halfway point in this mechanism again, so we've got this carbon-oxygen bond forming, as you have the carbon-bromine bond breaking or leaving, you can see that the ethyl and the hydrogen have been pushed away from where they originally were. You can see that relative to this bond here, the ethyl and the hydrogen are sort of to the left, whereas now in the halfway point we can actually say that the ethyl and the hydrogen are in the same plane as this bond. They're exactly halfway between this group and this group here. And then when the bromine leaves, it creates a gap on this side of the molecule that these 2 groups can move into, and that's what we see in the product. So here you go, the hydrogen and ethyl group, they've moved now, and relative to this bond they're actually on the right of the molecule. And it's the pushing of these 2 groups over to the other side of the molecule that we consider to be this inversion of configuration. And as I said in the lecture, it's kind of like an umbrella being popped inside out. And this is what happens every time you get an SN2 mechanism. So, we obviously needed to look at when you get an SN2 mechanism in preference to an SN1. So SN2 reactions usually occur when the carbon bearing the leaving group is relatively unhindered, so when you've got a primary or secondary alkyl halide, for instance. SN2 mechanisms tend to happen when the nucleophile you're using is a strong nucleophile. And hopefully you can see from the mechanism that the driving force for the reaction to happen is the strong nucleophile coming in and attacking the carbon of the alkyl halide. And finally, SN2 mechanisms tend to occur when the leaving group is a good leaving group. Cool, so that's a nice review of the important concepts in the SN2 mechanism. And then if you remember, I asked you in the lectures, is the SN2 mechanism the only mechanism possible? And of course the answer is no. And to illustrate this, we considered the reaction of tertiary butyl bromide with methanol to give this substitution product here. Now we observed that because this is a tertiary carbon, it's got 3 alkyl groups on it, there's too much steric hindrance here for attack of the nucleophile from the rear of the leaving group. We also observed that this is a really poor nucleophile. So both of these observations are suggesting that an SN2 mechanism, as we understand it, can't happen for this molecule, but we do actually see the substitution product forming. Furthermore, it has actually been shown experimentally that the rate of this reaction here doesn't depend on the concentration of the nucleophile, which is of course very different to an SN2 mechanism. So this tells us that overall this reaction is first order and not second order. So we can conclude from this that this reaction must be going via a multi-step reaction that involves an intermediate, because there's only one compound that's involved in the rate determining step. So that's a nice introduction to the second possible nucleophilic substitution mechanism, the SN1 mechanism. So of course this stands for substitution nucleophilic, and the 1 of course means that this mechanism is actually unimolecular at the rate determining step. So we need to actually explain this mechanism now. So if we have a generic molecule here with a good leaving group in here represented by L, what will happen in the first step of an SN1 mechanism is this leaving group will leave. You'll get heterolytic bond cleavage to generate a planar carbocation as shown here. Now this is a very, very slow process because this is not a stable product, this is a very reactive product. So this is the rate limiting step in an SN1 mechanism, the formation of the carbocation. Now the key word here is planar. These intermediates here can be thought of as kind of like an sp2 hybridized carbon, and therefore the 3 groups Z, Y and X have a trigonal planar geometry, so they're laying flat in one plane, and the positive charge you can consider as the sort of the p orbital of an sp2 hybridized carbon sitting above and below the plane of these 3 groups, that's completely empty and therefore really needs electrons. So this is a nice representation of a planar carbocation. It's like an sp2 hybridized carbon, so you've got your trigonal planar groups here and this empty p orbital which corresponds to the positive charge. And it's the formation of this species here that's the slow and therefore the rate determining step. Once you've generated the carbocation, you can then get reaction with the nucleophile. So again, you don't really need a very strong nucleophile now to react with this species, because these carbocations are very reactive. So even a nucleophile that's a neutral molecule that has a lone pair of electrons will react with this planar carbocation to give us our substitution product. And we can say therefore that the nucleophilicity of this nucleophilic species here is relatively unimportant, because the driving force for this reaction now is the reactivity of the carbocation. So there's some real key differences between this mechanism and the SN2. You can just go through that mechanism again, but for our actual example compound, this tert-butyl bromide. So again, the first step is that the bromide leaves the molecule to generate this planar carbocation here. Okay, as I said before, it's like an sp2 hybridized carbon. The positive charge is this empty p orbital. And then once this carbocation is formed, our nucleophile, in this instance methanol, is then able to react with it. So even though this is a really poor nucleophile, this oxygen will bond to this carbocation via its lone pair of electrons to give us this species here. And this reaction is a lot faster than this reaction because this is the rate determining step, the slow step. Once this methanol is added to the carbocation, to get our final neutral substitution product, what we have to see is this proton falling off and giving its electrons back to this oxygen here. And there you go, that gives us our neutral substitution product. So this is a classic SN1 mechanism. So if you look at the energy profile for an SN1 mechanism, we can see that it's got two transition states, here and here. And it's the first transition state that's the really important one, because it's the transition state that's at the highest energy. So it's this process here, getting over this energy barrier here, that's the slowest, and therefore the rate determining step. And of course, this corresponds to the formation of this carbocation intermediate. So now you can see that the carbocation actually sits slightly in an energy well here, and that's it's getting partial stabilization from these three alkyl substituents via electron donating inductive effects. And then the second transition state is for the reaction of this carbocation with the nucleophile, and this is a much smaller energy barrier, and this is a much faster step here, and then we go on to form our products. So this second transition state here is the reaction of the carbocation with the nucleophile, and is a much faster process. So, looking at this energy profile for the SN1 mechanism, we can say that the mechanism is unimolecular at the rate determining step, because this is the rate determining step here, and there's only this molecule involved in it. So the rate is dependent on how easily this carbocation is formed. And because this next step here is much faster, we can say that the rate is unaffected really by the nature of the nucleophile. And this is because these carbocations here are so reactive. Okay. So we've seen that the rate of these SN1 reactions are dependent on the generation of the carbocation, and that actually shows in the relative rates of these four different compounds here. We can see that this tertiary alkyl bromide here obviously reacts via an SN1 mechanism 1.2 million times faster than the secondary. So by far and away the fastest reaction is for this tertiary alkyl halide here. An SN1 mechanism can happen if you've got a secondary carbon bearing the leaving group, but of course, as you can see, this reaction is an awful lot slower than if you had a tertiary carbon. And then of course, as we can see here, that if you've got a primary or a methyl carbon bearing the leaving group, then these won't undergo an SN1 mechanism, because they won't be able to form the carbocation, because there's not enough stabilization from the electron donating alkyl groups. So that's a nice bit of experimental data of these relative rates of these reactions here. So now we need to go on and look at the stereochemical implications of an SN1 mechanism, because they're very different from the stereochemical implications of an SN2 mechanism. And we can say that the product of an SN1 reaction will usually be a racemic mixture. So again, if we were to start with an enantiomerically pure starter material, as represented by this generic structure here, the first step in the reaction is the loss of this leaving group to generate a planar carbocation. Okay, so you can see that all three of these groups are lying in this one mirror plane here. Okay, so this is this planar carbocation we've talked about. Now, because this molecule is flat, there's no selectivity over which side of this molecule the nucleophile attacks from. Now, if you get the nucleophile attacking from this side of the carbocation, you'll generate one enantiomer of the product. And then if you get the nucleophile attacking from the other side of the carbocation, you generate the other enantiomer of the product. So because of this mechanism, you're able to generate the two different enantiomers of the substitution product. And because there's such a vast number of these molecules in any one reaction, you're going to generate a statistical mixture of these two enantiomers here, because there's equal chance of attack from the nucleophile from this side of the molecule as there is for attack of the nucleophile from this side of the molecule. So overall, you're going to get a 50-50 mixture as a result of these two orientations of attack here. And that's the key stereochemical outcome from an SN1 mechanism. So, just to review what we've talked about, SN1 mechanisms are two-step mechanisms. They're unimolecular at the rate determining step. They tend to be promoted by low nucleophile concentration, or if you've got a weak nucleophile. And SN1 mechanisms are more likely to happen under acidic conditions. The key stereochemical outcome from an SN1 mechanism is that you get a racemic product mixture, and the rates of these SN1 mechanisms are much greater for tertiary alkyl halides compared to secondary alkyl halides, and we can actually say that primary and methyl alkyl halides will not undergo an SN1 mechanism. And we can say for an SN2 mechanism, this is a one-step concerted process that's bimolecular at the rate determining step, so the rate of the reaction depends on both the concentration of the electrophile and the nucleophile. SN2 mechanisms are promoted by high nucleophile concentration and also promoted by a very strong nucleophile, and an SN2 mechanism is more likely to occur under basic conditions. The key stereochemical outcome from an SN2 mechanism is you get complete inversion of configuration, and the rates of these SN2 processes are much faster for methyl alkyl halides and primary alkyl halides. They're very slow for secondary alkyl halides, and they won't happen for tertiary alkyl halides. So we can then use this observation that we've seen at the bottom of the previous chart to predict which mechanism happens. So we can safely say that if you've got a methyl or a primary alkyl halide, then any nucleophilic substitution is going to occur by an SN2 process. If you have a secondary alkyl halide, then of course you can get both of these processes occurring, and then you need to look at some of the other factors like the strength of the nucleophile, how good the leaving group is, and the concentration of the nucleophile. And if you've got a tertiary alkyl halide, then you're going to exclusively get SN1 nucleophilic substitution. Okay, so I'll point you in the direction of chapter 6 of the Jewett book if you want to do some background reading on this, and I hope this screencast helps. Cheers.